Hello everyone, I'm Minghan Zhu. This video will introduce you our work, Monocular Depth Prediction through Continuous 3D Loss. In the beginning, we provide an overview of this work. We proposed a novel loss function for monocular depth prediction, which better leverages the LiDAR measurements as source of supervision. Networks trained with this loss function produce depth prediction with higher accuracy and less shape distortion. This loss function is agnostic to network configurations. You can plug it in your existing network. The implementation is open sourced online. The task we're interested in is monocular depth prediction. Given an image, we want to predict the depth or range of each pixel. There are mainly two types of loss functions when training a depth prediction network. The first is geometric loss. For each pixel in the image, we penalize the difference between the predicted depths and ground truth depths at the same location. The second type is appearance loss. It penalizes the difference on corresponding image pixels found using the predicted depths. The mechanism can be explained by this figure, which are two image frames here. For each pixel location in the left frame, the possible pixel location of the corresponding 3D points in the right frame forms a line. If the depth is given, the pixel location in the right frame can be determined. The appearance loss supervises the depth by minimizing the difference of the corresponding pixel values. This is a simplified explanation of the existing loss functions, and there are some extensions to them, like ICP loss and structural similarity index measure. However, the overall idea is covered in this summary. We found that there are some limitations in the mentioned loss functions. In our scenario, LiDAR provides accurate range measurement. However, it is sparse and fails on glass and reflective surface. Take this point as example. We can see that the LiDAR does not have measurement at the corresponding area. For appearance loss, it is not reliable on homogeneous, cluttered, or non-Lambertian surface. Take the same point as example. We can see that the surface is reflective, so that the appearance across frames are not consistent. Both weaknesses point to the same problem. It is that the supervision is sparse, and it fails at certain areas consistently. In other words, there could be some certain types of area where no supervision is available, no matter how many data you collect and train on. We want to address this problem by viewing a point cloud as a continuous function. In this way, sparse LiDAR measurements could provide dense supervision. Here we show how it works. Given a LiDAR point cloud P, we construct a function f. Given a depth prediction from a network, we first back project the image to 3D space to generate a pseudo point cloud P tilde. Then construct a function f tilde from it. The supervision is aligning the function f tilde to a function f. Now the question is, how do you construct the function from a point cloud? Here we define a point cloud as a collection of points where each point has its 3D coordinate and optionally some other features. First, we define kernels for 3D coordinate and each feature. Theoretically, any positive definite kernels can be used. RBF kernel, exponential kernel, dot product kernel are some common examples. Then, we construct a function using these kernels. Each point corresponds to the product of all kernels with one argument specified at this point. Then we simply sum over all points in the point cloud. You probably want to ask why we construct functions in this way. It is because we want to leverage the property of reproducing kernel Hilbert space. Here we briefly introduce the background. A RKHS is a space of functions. It can be constructed by any positive definite kernel. Roughly speaking, such space contains all linear combinations of the kernel function with one argument specified at any location in the domain of the kernel function. RKHS is useful because it has a reproducing property, meaning that any function in the space can be evaluated by taking the inner product of the function and the kernel of this space. This property provides us a convenient way to calculate inner product between two functions. We just need to evaluate the kernel at each pair of input points and sum them all. Maximizing the inner product between two functions is exactly how we align two functions. From previous introduction, we know what the functions look like given point clouds. Now, we can define the continuous 3D loss function L C3D as negative inner product between f and f tilde. Specifically, we designed three kernels in our function construction. The geometric kernel takes the 3D coordinate of a pair of points as input. Closer points generates larger kernel value. The appearance kernel takes the color of a pair of points as input. Points with closer colors generates larger kernel value. The surface normal kernel evaluates the consistency between the local surface and the neighborhood area of the 2 points. The value is large when the local surfaces are smooth and when the normal direction of the pair of points are closed. By substituting the specific form of the kernels into the functions, we have the actual form of LC3D in this figure. More details, including the choice of hyperparameters, can be found in the paper. To show that the proposal loss function is not tied to any specific network architecture, we applied the C3D loss to three state-of-the-art monocular depth prediction networks, MonoDepth2, DORN, and BTS. One thing to notice is that MonoDepth2 is originally a self-supervised approach, not requiring any form of depth scrunches. On the other hand, BTS is originally trained with dense depth scrunches, which is available in Kitty depth dataset. However, our work emphasizes on making better use of raw LiDAR measurements as a supervision signal. Therefore, we use raw LiDAR depths for supervision in all three experiments for fair comparison. This table shows the advantage of our work. The three horizontal chunks correspond to comparison to three baselines. By simply adding the C3D loss in the training procedure, we observed up to 16% improvement in accuracy. The gray numbers correspond to result trained with supervision source as specified in the original paper. For example, MonoDepth2 originally used no depth scrunches. BTS and DORN originally used dense depth scrunches. We can see that the networks trained with dense scrunches still outperform our result. However, dense scrunches need careful post-processing from raw LiDAR and stereo measurements and cannot be trivially obtained for data out of Kitty dataset. Therefore, our proposed approach is valuable since it improves the accuracy when dense supervision is not available. We also want to show the effect of C3D loss in a more intuitive way. On the left, we show the RGB images and LiDAR scans. On the right, the depth prediction and converted surface normal direction from baselines and methods and from our approach are shown. We can see that our approach reduced the black hole effects due to lack of supervision at the car window area. Our approach also reduced the fake texture in depths inherited from RGB image and generated smoother surface, which is more apparently shown in surface normal images. By back-projecting image pixels to 3D view, we can get a better look at the quality of depth predictions. By incorporating the C3D loss, the predicted depth has better preserved shapes with less distortion. The depth prediction on glass and reflective surface is especially improved. This is a short demo showing the depth prediction from the video. It shows that applying the C3D loss helped the network produce higher quality depth predictions with less shape distortion. In summary, we propose a novel continuous 3D loss function for monocular depth prediction. We address the problem of sparseness in existing supervision signals and handle it by viewing point clouds as continuous functions. The proposed C3D loss improved the accuracy upon several state-of-the-art networks as baselines. It improved the prediction quality on non-Lambertian surfaces and reduced shape distortion. For more information, please visit our page. Thanks for your attention.